Good morning, all my calculus lovelies. This is Mr. Hammer in front of a ficus. I'm teaching a little bit today about logarithmic differentiation. It's a whole lot of fun, and I'm sure you guys are going to enjoy it just wildly. So what I'd like to do is we're going to just kind of begin by looking at two problems and talk, first of all, why you use it. And then second of all, go through how you use it. So let me start by sharing my screen and showing you the two problems. These are actually from your homework. So I need to present to you this window. And let me share. So here you go. We have two problems, and let me kind of zoom in on these for you. So first of all, we are going to talk about when you use logarithmic differentiation. And these are actually two really good problems that explain when you would use it. So this first one, the reason you would use it is because x is in the exponent. If you take a look here, you will notice that it's sine of x, but we also have to the x power. What this is going to allow us to do if we use the rules of logarithms, it's going to allow us to take that x out of the exponent and make it multiplication. So that is a really important thing when we are taking derivatives of functions. So whenever you get a weird function and the x is in the exponent like that, logarithmic differentiation sometimes might be a really helpful tool. The other reason is when you have complex fractions. Okay, I mean, if you take a look at this, notice we have a lot of very complex fraction stuff going on here. It's also under a fifth root and things like that. So it just makes everything very complicated. So whenever you get complex, and these are called rational functions. Whenever you get a complex rational function like this, you're going to want to do logarithmic differentiation. There's just no getting around it. So we're going to start by doing the first problem. And we're going to go through and going to kind of figure out the derivative for this. And then I'm going to show you the really complicated one, this one. But I'm going to show you how logarithmic differentiation allows us to do that a little bit easier. Now, please remember, there are some rules that you need to know and things like that. So remember, for logs, if you have two functions that are being multiplied together, remember you can split them up into addition. That's really important. The other rule is, remember, if you have two functions being divided, remember this is now the natural log of m minus the natural log of n. Okay? Another important one is if you have the natural log of some function to the n power, this allows us to now take the n out front and multiply it by it. Okay, these are the big three that we're going to be using here in these problems. We have no logs, so we do not need to use the log function. So let's start by looking at this one. If we take a look at this, we're going to be doing some implicit differentiation as well as using the logs. So I notice here that, oh, the x is in the exponent. So right away, what I'm going to do is I'm going to take the natural log of both sides. Okay? Now, by doing so, that now allows me to go like this. The natural log of y equals, I can now pull the x out to the front, natural log of sine of x. Okay? So here's what we have to do. Okay? We are now going to go through and we are now going to take the derivative at this point. So the natural log rules are used in the beginning before you take the derivative. Reason being is it allows us to change the equation just a little bit and allows us to use more of the rules that we have. So let's start now by doing the derivative process. So first of all, you do have to take the derivative of this side. So the derivative of natural log of y is going to be 1 over y. But remember, you also have to multiply that by y prime. Okay? Now, on the other side, we've got kind of a lot of stuff going on here. Okay? We have the product rule with a little bit of chain. Because notice, we have those two things multiplied together, but we also have sine of x inside the parentheses there. So we're going to use the chain rule to do our work on the other side. Okay? So we're going to do the first times the derivative of the second. So we're going to go x. Now, times the derivative of the second, but notice this is a chain rule. So I'm going to kind of just move down here a little bit and just do my work off to the side. And I'm going to follow sort of the chain rule. So I'm going to go, my outside is the natural log of x. The inside is sine of x. Okay? So when we go through and we take the derivative of natural log, of course, is 1 over x. And the derivative of sine of x is cosine of x. So when I do all of my chain rule stuff, I end up with 1 over the sine of x times the cosine of x. Or, of course, we can just simplify it to cosine of x over sine of x. Okay? So I'm going to put that in this space right here. So I'm going to do cosine of x over sine of x, because it's the first times the derivative of the second. Now I need to add to that the second, so we're going to do natural log of sine of x times the derivative of the first, which is x, so that just becomes 1. Okay? So here's what we now have to do. We now have to isolate the y prime. Okay? So we now have to isolate this y prime sort of thing. So we're going to multiply both sides by y. So notice I am multiplying both sides by y. So what I'm going to end up with is y prime equals x cosine of x sine of x plus the natural log of sine of x all times y on this side. Okay? Now, the issue is we can't have a y over here because they want it only in terms of x. So we need to go back to our very beginning, and we know what y is. We know y is sine of x to the x power. So I'm going to replace this with sine of x to the x. So our final answer is going to be y prime equals, and it's very complicated, cosine of x sine of x plus the natural log of sine of x, all of this times sine of x to the x power. And there is your final answer for just this first problem. Okay? So when you go through and do this, you need to make sure that you use logarithm rules to make it a little easier to use the derivative rules we have, and then just start plugging your way through it. Okay? But notice it is an implicit differentiation problem. You do have to take the natural log of both sides of the equal sign. So